In section 3.4, we look at real zeros of polynomials and solutions of equations. So in the first example, we want to use a known zero to factor a polynomial. So it says to show that x equals 4 is a zero of this polynomial, and then use this fact to completely factor p of x. All right, well, if we know that x equals 4 is a zero to the polynomial, then that means when we use synthetic division with the number 4, we should get a remainder of 0. So here I have set up the synthetic division process. Let's go ahead and do the synthetic division. 4 times 3 is 12. Negative 4 plus 12 is 8. 4 times 8 is 32. Negative 48 plus 32 is negative 16. 4 times 16 is negative 64, and sure enough, 64 minus 64 is 0. So keep in mind what this means. If x equals 4 is a zero of the polynomial, then this means that x minus 4 is a factor. Also, we know that this polynomial, represented by those coefficients, which is 3x squared plus 8x minus 16, is also a factor. And this means that the original polynomial 3x cubed minus 4x squared minus 48x plus 64 can be factored into x minus 4 multiplied by 3x squared plus 8x minus 16. So what's important to note here is that we used synthetic division to help us factor a polynomial. Now again, keep in mind, you only get factors when the remainder is 0. But they want us to factor this polynomial completely. So what we're going to do is we're going to take this other factor and we're going to factor it. But to do that, we don't have to use synthetic division. We can just use our good old factoring technique. We can use the magic x. 3 times negative 16 is negative 48. And we put the number 8 in the middle. And now we just need to think of two numbers that have a product of negative 48 and a sum of 8. And those two numbers are 12 and negative 4. So 12 times negative 4 is negative 48, and 12 plus negative 4 is 8. So when we go to complete this factorization, we are going to break this down into the product of two binomials. And we know that we're going to start by doing x plus 12 and x minus 4. But then remember the trick. When you have a coefficient here, you have to divide each one of those by that coefficient. And in doing that, we end up getting the first factor there. And then this one simplifies to x plus 4. And then for the second one, since you cannot divide 4 and 3, we're going to move that in front of the x there, which gives us 4x minus 3. So the complete factorization of that polynomial is x minus 4 times x plus 4 times 4x minus 3. Now, I should also mention that we also know the other zeros of the polynomial. So we started with the knowledge that x equals 4 was a zero of the polynomial, and we used that to factor the polynomial. But once you have all of its factors, we can then list all of the zeros. So again, we know that x minus 4 gives us a zero of 4, and the reason for that is because when you set x minus 4 equal to 0, you get 4 when you solve the equation. X plus 4 gives us a zero of negative 4, and that is because when you set x plus 4 equal to 0, solving for x gives you negative 4. And finally, the last zero is positive 3/4, and this is because when you set 4x minus 3 equal to 0, and you solve this equation, first you add 3 to both sides, and then you divide by 4, and you get 3/4. So when you know the factorization, you also know the zeros. They are very, very closely related to each other. So now we summarize all that information with the following. Let p of x be a polynomial function. Let c be a real number. Then the following statements are equivalent. That is, if one of these statements is true, then the other two statements are also true. Also, if one of the statements is false, then the other statements are false. So here are the statements. P of c is equal to 0. X minus c is a factor of p of x, and the point c0 is an x-intercept of the graph of p of x. So if you know that c is a 0 of the polynomial, that means that x minus c is a factor. We just talked about that in the previous problem. And that also coincides with c is an x-intercept of the graph. We talked about that in a previous section. So in this next example, we just want to fill out the chart. It tells us that we have 3 functions, p of x, h of x, and g of x. And for each one of these, they give us some information, and we are to fill out the rest of the squares in the chart. So for p of x, they tell us that the point 5, 0 is an x-intercept. Well, if 5, 0 is an x-intercept, then that means the number 5 is a 0 of that polynomial. And it also means that x minus 5 is a factor of the polynomial. For h of x, they tell us that x minus 3 is a factor. If x minus 3 is a factor, then x equals 3 is a 0. And the x-intercept will be the point 3, 0. And finally, for g of x, they tell us that negative 1 is a 0. That means that the point negative 1, 0 is an x-intercept, and x minus negative 1 is a factor. And of course, x minus negative 1 is also the same as x plus 1. So if you know the zeros of a polynomial, you know the factors, and you also know the x-intercepts. So all 3 of those things are basically synonymous with each other. Before we talk about the next concept, I want you to consider the polynomial function p of x equals 10x squared minus 29x minus 21. If you were to factor this polynomial, you would get the factors 5x plus 3 and 2x minus 7. So if I asked you for the corresponding zeros to the polynomial, you could get this by simply taking each factor and setting them equal to 0. And then you would solve each of these equations, and in the first equation you get negative 3/5, and in the second equation you get 7 over 2. Now what I want you to notice is that if you look at the denominators of each of these, you'll notice that the denominators are 5 and 2. And 5 and 2 come from 10. Those are the factors of 10. And if you look at the numerators, 3 and 7, those are the factors of 21. And this is not a coincidence. So the zeros of a polynomial function will have a numerator that has to be a factor of the last number in the polynomial, and it will have a denominator that has to be a factor of the first number in the polynomial. And really what I should say is that the numerator should be a factor of the constant term, and the denominator should be a factor of the leading coefficient. So that's summarized in the rational zero theorem, which you can see down here. The rational zero theorem says if f of x is equal to a polynomial function, and if all of these coefficients are integer coefficients, so no fractions, and p over q is a rational zero, then p is a factor of the constant term, and q is a factor of the leading coefficient. So that's basically exactly what I said up here regarding these two solutions. The other fact is that the number of real zeros of a polynomial is at most the degree of the polynomial. So if you have a non-constant polynomial function of degree n, it will have at the most n real zeros if you count them according to multiplicity. So a quick example of that is, this is a second degree polynomial. So its degree is 2, and you also notice that it has 2 zeros. So it is impossible to have more than 2 zeros for a second degree polynomial. So this is good information to know. So in the next example, we want to apply the rational zero theorem and find all the zeros of the polynomial 3x cubed minus 6x squared minus x plus 2. So what you do is you say, well, if we have zeros, rational zeros, we know that the numerator of those zeros has to be a factor of the number 2. And the factors of 2 are 1 and 2. And the denominator of those zeros has to be a factor of 3. And the factors of 3 are 1 and 3. So if you have a rational zero, it has to be a combination of one of these two numbers divided by one of these two numbers. And also it can be positive or negative. So the possible rational zeros are going to be 1 divided by 1. So that's going to be plus or minus 1. The other possible rational zero is 2 divided by 1. So that'll be plus or minus 2. And then we can also do 1 divided by 3, which is plus or minus 1/3. And finally, 2 divided by 3, which is going to be plus or minus 2/3. So if we have a rational zero, it has to be one of these 8 numbers. That's very useful because when you try to find the rational zeros, what you're going to do is set up a synthetic division problem. That's what I'm doing here. And then the important thing you have to do is you have to guess what number to put in the box. Well, the only numbers you're going to try to put in the box are going to be one of these numbers. You're not going to try anything else because we know that other rational numbers won't work. So the way I always start these problems is I just start with the simple guess of trying 1, the number 1. Let's see if that's a 0. So 1 times 3 is 3. Negative 6 plus 3 is negative 3. 1 times negative 3 is negative 3. Negative 1 and negative 3 is negative 4. And 1 times negative 4 is negative 4. And that gives us a remainder of negative 2. So we know that positive 1 is not a 0 of this polynomial. So what I can do now is I can just start over. I'll erase all the math that I did here. And I'll pick a new guess. And my next guess is I'm just going to try negative 1. So I tried positive 1, that failed. Now I'm going to try negative 1. Let's see what happens. Negative 1 times 3 is negative 3. Negative 6 and negative 3 is negative 9. Negative 1 times negative 9 is positive 9. And adding that gives us positive 8. And negative 1 times 8 is negative 8. And that gives us a remainder of negative 6. So that also failed. So we now know that neither 1 nor negative 1 is a 0 of this polynomial. So it can be a little frustrating because you do that work and you still don't find anything. But now we're just going to go to the next number. Let me try x equals 2. Let's see, 2 times 3 is 6. Negative 6 plus 6 is 0. 2 times 0 is 0. Negative 1 plus 0 is negative 1. And 2 times negative 1 is negative 2. And negative 2 plus positive 2 is 0. So that's a success. So what are the zeros? Well, we know that one of the zeros is x equals 2. Now, how do we find the other zeros? Well, let's remember that when you start with a polynomial, like the one we have here, since we got a remainder of 0 here, we know that x minus 2 is a factor, and we know the other factor is from these coefficients here, and that gives us 3x squared minus 1, right? So this is 3x squared plus 0x minus 1. Now, how do we get the other zeros? Well, there's a couple of different ways you can do it, but the easiest way to do it is you would first try to factor this. Now, this doesn't factor easily because it's not the difference of two squares, but notice that if you take that factor 3x squared minus 1 and you set it equal to 0, you can solve for x by simply adding 1 to both sides, dividing by 3, and then finally taking the square root of both sides, which gives you x equals plus or minus the square root of 1/3. And that's plus or minus the square root of 1 over the square root of 3. The square root of 1 is 1, and so we end up getting plus or minus 1 over radical 3. And if you rationalize the denominator by multiplying by radical 3 over radical 3, we get x equals plus or minus radical 3 over 3. These are the other two zeros. So in the end, we know that our zeros are 2, radical 3 over 3, and negative radical 3 over 3. Now I want you to notice that only x equals 2 is a rational zero. The other two zeros are irrational zeros. And they're irrational because radical 3 over 3 is an irrational number. So that doesn't violate what we said in the beginning. What we said in the beginning is that any rational zeros that we would find would have to be one of these numbers. And so x equals 2 is one of those numbers. But the other two zeros aren't rational. They are irrational. And we can find those by solving a simple equation, or sometimes you can find them by factoring. And if all else fails, you can find them by using the quadratic formula. Now the next example, it says to use a graphing utility to locate the zeros. And then I want you to notice that this polynomial is the same as the one that we just did. Now there are many graphing utilities that you can find online. I found one and I have it on my iPad. And if you graph the function p of x, this is what it looks like. So you have a third degree polynomial function. And then what I did is I touched the x-axis at all the points where it crosses, and that gives you the zeros. So I want you to notice that one of your zeros is x equals 2. The other zero is this number here, which is 0.577, and the final zero is negative 0.577. And it turns out that 0.577 is approximately equal to square root of 3 over 3, and negative 0.577 is approximately equal to negative square root of 3 over 3. And this is consistent with what we found on the previous page. So this is just emphasizing the fact that if you have a graphing utility, that graphing utility can be very useful in helping you find zeros of a polynomial. Because again, zeros of a polynomial is synonymous with x-intercepts. So remember that. The zeros of your polynomial are the same as the x-intercepts of the graph. In our last example, they ask us to solve the equation 3x to the fourth minus 8x cubed minus 9x squared plus 22x is equal to negative 8. So the first thing I'm going to do when I have a higher degree equation like this is I'm going to set the equation equal to 0. To set this equal to 0, all I need to do to both sides here is add the number 8. And when we do that, we end up getting this equation. Now, I want you to notice that this is just a polynomial. So if you want, I can give that a name. I can call that P of x for polynomial. And what I'm doing here is I'm trying to figure out where is the polynomial P of x equal to 0. So this is nothing more than finding the zeros of the polynomial. That's all we're trying to do. So solving an equation is the same as setting the equation equal to 0 and finding the zeros of that function. So to do this, we can use synthetic division. If I set up the synthetic division process, we have this, and then now I need to guess what number to put in the box. Well, we're not going to make random guesses. We're going to take educated guesses. If we're thinking about rational zeros, the only possibilities that we have, they will have to be factors of 8. So what are the factors of 8? 1, 2, 4, and 8 are the factors of 8. And we have to divide that by the factors of 3. And the factors of 3 are 1 and 3. These are all of our possibilities. Now you can write all those out. So what we have is plus or minus 1 divided by 1, plus or minus 2 divided by 1, plus or minus 4 divided by 1, and plus or minus 8 divided by 1. So I just took each of these and divided it by 1. But then we can also divide all of these by 3, and that gives us plus or minus 1/3, plus or minus 2/3, plus or minus 4/3, and plus or minus 8/3. So these are all the possible rational zeros. And that can seem a little bit overwhelming, but remember, this is what? This is a 4th degree equation. So this can have at most 4 zeros. So it's not going to be all of these numbers. It's just that these are the only numbers that are possible. So when you go to do this, you're going to start, I recommend you start by trying to guess a whole number here. And I always like to start with the number 1. So let's go through the process. 1 times 3 is 3. Negative 8 plus 3 is negative 5. 1 times negative 5 is negative 5. Adding those, we get negative 14. 1 times negative 14 is negative 14. 22 minus 14 is 8. And 1 times 8 is 8, and that gives us 16. So we were very close to finding a 0 there, but unfortunately, that was not one of them. So we erase that and start over. So now I'm just going to guess negative 1. Negative 1 times 3 is negative 3. Negative 8 plus negative 3 is negative 11. Negative 1 times negative 11 is positive 11. Negative 9 plus 11 is 2. Negative 1 times 2 is negative 2. 22 take away 2 is 20. And negative 1 times 20 is negative 20. And that gives us negative 12. So we notice that negative 1 also doesn't work. Now, the reason I'm picking ones that don't work is because I want you to understand that this is likely how it will be for you when you're doing homework. You don't always guess the right answer on the first try. So you might be doing a little bit of erasing. So negative 1 and positive 1 both did not work. So next I'm going to try 2. 2 times 3 is 6. Negative 8 plus 6 is negative 2. 2 times negative 2 is negative 4. Adding those, we get negative 13. 2 times negative 13 is negative 26. If I add those, I get negative 4. And 2 times negative 4 is negative 8. And negative 8 plus 8 is 0. So this is a success. We have found our first 0, and that first 0 is the number 2. Now, the beauty of synthetic division is that I can now just take these numbers and start a new synthetic division problem. Now, what you can do is you can rewrite it and start making your next guesses here. But you can also just piggyback the next synthetic division right on top of the one that you just did here. So as long as you get a 0, I can just say, now we're going to bring that 3 down, and we're going to make another guess right here. Now, when I make the next guess has to be a factor of 4, right? Because now my polynomial that I have left over, the constant term is of 4. So I could try 2 again. Let's see if 2 works. Sometimes it works more than once. 2 times 3 is 6. Negative 2 plus 6 is 4. 2 times 4 is 8. Negative 13 plus 8 is negative 5. 2 times negative 5 is negative 10, and that leaves us with negative 14. Okay, so that was a failure. That did not work. So we don't have to try the number 2 anymore. Let's try negative 2. Negative 2 times 3 is negative 6, which gives us negative 8. Negative 2 times negative 8 is positive 16, which gives us 3. And negative 2 times 3 is negative 6, which gives us negative 10. So that also did not work because we did not get 0. So from here, you could try a number like 4 or negative 4. Let's go ahead and try 4. 4 times 3 is 12. That gives us 10, and then 40, and that's 27. Okay, this is just getting way too big, right? This is 108, and this is 104. So that didn't work. All right, so what's happening? What can we do next? Well, remember what your possibilities were. These were the possibilities, and we already saw, we got 2 to work once, but negative 2 didn't work, so we're done with those. We tried positive 4, that didn't work. We're not going to try 8 anymore because we don't have 8 as our last number, right? Our last number is now a 4, right? So it looks like the other rational 0 is probably one of these fractions, which is kind of a bummer because fractions aren't really that fun. So I'm going to try that first fraction, which is 1/3. This can get a little bit tedious, so you got to be careful. 1/3 times 3 is 1. Negative 2 plus 1 is negative 1. 1/3 times negative 1 is negative 1/3. Negative 13 and negative 1/3 is going to be negative 40 thirds. 1/3 times that is negative 40 over 9, and this is definitely not 0. Okay, so that didn't work. Okay, but don't lose your patience. Just keep on going. We tried 1/3. That didn't work. So next, let's try negative 1/3. Negative 1/3 times 3 is negative 1. Negative 2 plus negative 1 is negative 3. Negative 1/3 times negative 3 is positive 1. Negative 13 plus 1 is negative 12. And negative 1/3 times negative 12 is positive 4. And negative 4 plus 4 is 0. Aha, success. So now let's think about what we've done. We have the original polynomial, 3x to the 4th, minus 8x cubed, minus 9x squared, plus 22x, plus 8. We now know, since 2 was a 0, x minus 2 is a factor, and since negative 1/3 is a 0, x plus 1/3 is a factor, and the remaining factor comes from this here, and that is representing 3x squared minus 3x minus 12. Once I get it down to a quadratic that is remaining, that is a second degree, I don't have to use synthetic division anymore. I can use normal factoring techniques. So watch carefully what happens here. I'm going to factor the 3 out of all of these. If I pull that 3 out, I get x squared minus x minus 4. And I can find the remaining zeros by finding the zeros of that quadratic. Now, another little tip I want to show you here is if I take the 3 that I factored out of here, I can take that 3 and I can choose to distribute it to this one. And if I do that, we get quite a nice result here. We get x minus 2, and then this becomes 3x plus 1. So you see, multiplying these numbers by 3 will get rid of that fraction and make your factor look a little bit nicer. So now to get the other zeros, I need to take this quadratic and set it equal to 0. And unfortunately, that does not factor, so I have to use the quadratic formula. And so I'm assuming that we all remember the quadratic formula. And if you simplify that, you're going to get x equals 1 plus or minus the square root of 1 plus 16, all divided by 2. This is 1 plus or minus the square root of 17 divided by 2. And so we have 2 zeros there. One of them is 1 plus radical 17 divided by 2. The other one is 1 minus radical 17 divided by 2. So those are the 2 zeros that we get from this factor. And then remember, we already had x equals 2 and x equals negative 1/3. So we have a total of 4 zeros of the polynomial. And that means we have a total of 4 solutions to the equation. Because remember, in the beginning, we were just trying to solve that equation. So 2 of our solutions are rational. Okay, that means fractions or whole numbers. And the other 2 solutions over here are irrational.